The alternating series remainder is a way for us to approximate the sum of these alternating series when we can't actually calculate the sum themselves. It is really a statement of our error and lets us know how close we are to the actual sum even though we can't calculate it. So if a convergent alternating series satisfies the condition where a sub n plus 1 is less than or equal to a sub n, in other words, a non-increasing function or series, then the absolute value of the remainder, r sub n, involved in approximating the sum s by s sub n is less than or equal to the first unused term. All right, that's a lot of letters, so let's talk about what these mean. Okay, you already know that the a sub n plus 1 and the a sub n, those are just discussing the terms. So the subsequent term is going to be less than or equal to the former term. And then the absolute value of the remainder r sub n, that's the remainder. In other words, that is approximately what's left from the sum that we calculate and the actual sum itself. It is an approximation. It's going to give us an interval of that this sum will fall in. Okay, so this just is giving us the error from which our sum is off by the real sum. Okay, so we're going to be using that to approximate S, the sum. That stands for the actual sum of the series, and then S sub n is just the nth partial sum. So it could be S sub 3, which would be the third partial sum, or the sum of the first three terms. It could be S sub 10, the sum of the first 10 terms, the nth partial sum. So that's what each of those letters means. Okay, so in other words, the absolute value of the sum of the series minus the nth partial sum is going to equal the remainder. And there's a typo there. That should be the absolute value of the remainder. And so the sum minus the nth partial sum is going to equal the absolute value of the remainder. And that should be less than the next unused term, or the next term. So if I am using the third partial sum to estimate our sum and get the remainder, then that means that the remainder after the third partial sum would be less than or equal to the fourth term. If I used the 10th partial sum, so I got a remainder after that, then I would have a remainder less than or equal to the 11th term itself. Okay, and that, again, that's the absolute value. All right, so we need to keep that in mind. Just for example, our a series that we've summed up, or not summed up, but we've determined the convergence of recently, is alternating over n. And if you remember, then this became, we could rewrite this as negative 1 to the n times 1 over n. N equals 1 to infinity. Okay, a sub n in this case is 1 over n. And so what we're saying here is if I calculated the first 6 terms and added them up, then I could approximate the sum from that. And my remainder that I would get would be actually less than the 7th term. Okay, so that's kind of what we're looking at, and hopefully it makes some sense, but it may take us going through an example for it to sort of sink in what we're saying here. So let's go ahead and look at our example. We're going to approximate the sum of the series from 1 to infinity of negative 1 to the n plus 1 times 1 over n factorial. And we're going to use the first 6 terms. Okay, so in this case, a sub n is 1 over n factorial. And the first 6 terms of this series, so when n is 1, then a sub 1 is going to be 1 over 1, because the exponent there is going to be a 2. And 1 factorial is just 1, so that's going to equal 1. Alright, a sub 2 is going to be negative 1 to the 2 plus 1, which is negative 1, because that's negative 1 to the third. And it's going to be 2 factorial, which is just 2 times 1, and so that's going to be negative 1/2. The third term will be positive 1 over 3 factorial, which is 1 over 6, because that's 3 times 2 times 1. A sub 4, negative 1 over 4 factorial, which is negative 1 over 4 times 3 times 2 times 1, which is 1 over 24. A sub 5 is 1 over 5 factorial, and a sub 6 is negative 1 over 6 factorial. So you're seeing how each of those goes. Okay. All right. So we want to approximate the sum by the first 6 terms, so we're going to sum up all of these. Okay, and so if you keep summing these up, and you could use your calculator, I mean, you could do it by hand, but you can do it by your calculator, then you're going to get, when we sum them all up, and with the alternating signs, we end up getting 0.63194. So we'll call this sum S sub 6, because that's the sum of the first 6 terms. Now the absolute value of our remainder in these first 6 terms is going to be less than or equal to the 7th term, because that's our first unused term. Okay, and so a sub 7 is simply going to be 1 over the absolute value, the 7 factorial. And that equals 1 over 5040, or it's approximately 0.0002. So why do we care? Well, the reason why we care is because, according to our theorem that we looked at, the sum minus our nth partial sum, in this case the 6th partial sum, is equal to the remainder, the absolute values of all of that. But we can actually rearrange this. Okay, so let me erase. And it's not going to let me erase, so let me just write it over here. Okay, so if I have S, the absolute value of S minus S sub n equals the absolute value of R sub n, then I can move some things around, and I'm going to end up with the sum is going to equal the remainder minus our partial sum. Okay, but that remainder ends up, in this case, was smaller than that. Those absolute values are going to let me reverse that. So I'm going to have the absolute value of the sum is going to equal the partial sum minus the remainder. Erase that, wasn't equals. And so we'll be able to sort of get an idea of what that sum is going to be. All right, so let's go back down here. And so let's take our partial sum here, 0.63194, and I'm going to subtract 0.0002. And this is going to be one of the bounds of my sum. Okay, so this will make it be smaller. So this is what the smallest that the sum could be of this particular series. How do I find the upper bound? Well, because these are alternating, because these terms alternate, and because of the absolute values, we could also consider the case that maybe it's actually going to get bigger. Okay, and so we would add our remainder. Quite simply, what we have is the sum is going to be an element of S sub n minus R sub n, comma, S sub n plus R sub n. Okay, oops, that should be a closed bracket. And so that that is the interval over which we are going to find our sum. I have no idea why that's not letting me erase. This program is strange. Okay, so it looks like that. All right. So what we know then is that our sum for this particular problem is going to be from 0.63194 minus 0.0002 to 0.63194 plus 0.0002, or in other words, the sum of this series is going to actually fall between 0.63174 and 0.63214, and that's our range. And I actually need to be making this an element of instead of equals because it's an interval. Okay, so our sum is an element in there. We don't know what it is, but what we've done is we've narrowed it down, and we know that the sum of our given series up here that we were trying to evaluate is going to fall between these two numbers. So what happens as I take more and more terms and sum them up, right? You're going to get a smaller and smaller interval each time. So if we calculated this to the 10th partial sum, our interval would be even smaller. The 100th partial sum, our interval would be even smaller, and so we can just sort of narrow in on what the sum is without actually finding what that exact value is. So we're lessening the error the more terms we use. Okay, practice some of these problems. I know I was kind of going through it. It maybe wasn't the best explanation, but hopefully you see what we're doing here. Let me know, email me, put a message on the Blackboard, or ask me in class tomorrow, and we'll do some more and work on these until you got it.